Hey, physics class. So when we left off, we had symbols and terminology for batteries, wires, and resistors so that we could draw simple circuits kind of like this one. Let's go ahead and draw one. So if I have a battery here, let me have a wire. It comes around. It's not closed because I'm going to put in there a resistor. Okay, so just so we are remembering that the units for the energy supplied for the electrical pressure supplied by that battery are volts, and AA batteries are 1.5 volts, but let's go with another kind of battery today. Let's go ahead with a 9 volt. So we got 9 volts, and for a resistor, oh, let's have a fairly high resistance this time. Let's have this resistor be 1000. Now, ohms are just like any other unit. If you want to have 1,000 of them, you can just convert it to a kilo version of it. Of course, significant digits are lost there, but when it comes to significant digits, the math rules are going to get really kind of complicated and lost here. So if you've been doing significant digits up until this point in this unit, we're basically just going to abandon them. So maybe that makes you happy. Anyway, we've got a 9-volt battery. We've got a 1,000 ohm resistor. And let's just go ahead and quickly compute the current in this circuit. Remember Ohm's law. That would be voltage equals the product of the current and the resistance, which means that I've got 9 volts equals unknown current times 1,000 ohms. In order to solve this, I would need to divide both sides by 1,000, and so I end up with 9 thousandths. Now, again, if you have 1,000th of something and it is a standard metric unit, you should be able to convert that to the milli version of it. So let's just go ahead and call that 9 milliamps. So that is a capital A for amps. So if you're going to have milliamps, you should have a lowercase m and a capital A. All right, great. So what exactly do we mean when we say a current? So now I want to remind you of this. So this was the source of water pressure that I was using to demonstrate the flow of electricity, and voltage being how much urgency the electricity is flowing with. Well, water pressure is like the urgency with which the water is flowing. So voltage and pressure are analogous. So let's see. If voltage is kind of like pressure, then what would current be? Well, current refers to the amount of electricity that is flowing. You might say, in terms of the water analogy, it would be the volume of the water that actually was flowing. So I'll call it volume. So think of it kind of like this, back on this. So this syringe has marks at various numbers of millimeters. And if I were to make all 5 of those millimeters empty, well, how hard I was squeezing on it would be related to how long it took for that water to go through. So if I squeezed really hard, I'd get that 5 milliliters out almost immediately. If, on the other hand, I was barely squeezing at all, it would take me a while. The current just refers to the rate at which a certain volume of water is flowing. Okay, well, that is just a side note to add to the last video lesson. But now I want to move on to something else. Okay, so we talked about what current is. So the next question is, what about resistance? Now, when I demonstrated resistance with the water, I used a paper towel jammed in the end of the hose to inhibit water flow. Basically, it just had to be something that the water would have to work extra hard to get through. Now, that is a little odd because having a paper towel jammed into a tube is not a very common occurrence. It would make more sense, say, if there was a filter that the water had to run through. But I think that there's actually an example that would fit the description a lot better. And that has to do with something that there isn't a lot of these days, and that would be traffic. So this isn't going to be a closed circuit, so in that respect it'll be different from an electrical circuit. However, it's still the flow of something through a conduit, so let's just go ahead with that. Let's say we've got a bunch of cars that are all traveling from point A to point B. So that could be from, home to work or from one city to another. It doesn't really matter. We just need to have a point A and a point B. Okay, so if you've got 2 paths between point A and point B, let's say we've got in green a big highway. It's well paved. It's got 6 lanes. It's a really, really high volume highway. And then the other possible path is a windy dirt road full of potholes and blind turns and possibly even like some monsters or something that'll jump out and, use your imagination. So, dirt road. Okay, so we got a whole bunch of cars that are going from point A to point B. Which road is going to take them on that trip first, fastest, best? So that's a pretty obvious answer, the highway. So if everybody is a sensible driver, they should take the highway. But here's the deal. If everybody takes the highway, then the highway gets crowded. And if the highway gets crowded and there's a lot of traffic, then all of a sudden it's not as good of a route as it used to be. At some point, might it actually be to your advantage to take the dirt road because the highway is so packed? Well, there is some math to it. So let me be a bit more specific with it, okay? Rather than just having highway and dirt road. I'm going to put some numbers to it so we can do some calculations. So let me redo this, but in every case, the green path is going to be the nice one, and the red path is going to be like the slow one. So let's try this again. A and B. And we're going to do it like this. The green path is capable of transporting 100 cars per hour. The red path is capable of transporting 50 cars per hour. Okay. Now, here's how we're going to quantify this. Let's say we have 200 cars that we want to transport from point A to point B. I'm going to pose this question to you, and I want you to pause the video, work it out for yourself, and then come back and resume the video when you've finished. I want to know how long would it take. Actually, let me write that down. I want to know how long would it take if everyone took the green road. That's everyone. How long would it take if everyone went on the red road? And then I want you to find what you think is the best way to split up the traffic to get everyone over in the shortest amount of time. I guess we can call that number 3. Okay, so once again, just have everyone go on the green road, see how long that would take. Just have everyone go on the red road, see how long that would take. And then I want you to try to work out what's the best way to split up the traffic and how long will everyone get over in that arrangement. Go ahead and do that, and when you're done, resume the video. Alright, so the problem as stated had point A with a poorly drawn circle leading to point B with a nicely drawn circle. One path, colored green, transports cars at a rate of 100. The other path, colored red, transports cars with a rate of 50. Okay, so if we are trying to transport 200 all on the green road, it's going to look like this. All green, we've got 200 cars. We're going to divide that by 100 cars per hour. So 200 cars divided by 100 cars per hour. That equals 2 hours. Okay, what if everyone takes the red road? If everyone goes red, we're going to have not enough room for this fraction. We're going to have 200 cars, 200C, I'll just abbreviate that, 200 cars over 50 cars per hour. That's going to be 4 hours. And no surprise there. The slower road takes more time, and in fact, it's half as fast, so it takes twice as long. Okay, so that's not really a surprise. Let's try to work out the best path. So let's just kind of take a guess and see where that takes us. What if we could make half the cars go on the green road and half the cars go on the red road? Split them up evenly. How long does that take? Well, 200 cars split into two groups. Each group would be 100 cars. So let's see. If we have 100 cars on the green road at 100 cars per hour, well, that's going to take 1 hour. If we have 100 cars on the red road at 50 cars per hour, that's going to take 2 hours. Okay, so it turns out that wasn't any better than everyone taking the green road. And here's why. Everyone who took the green road, who got over there in an hour, they're going to be waiting for everyone on the red road to finish their trip. So the reason that that doesn't work or can't be the best is because we're wasting time. Some of the green road drivers just waiting at point B for the red road drivers to hurry up and finish. So the lesson that this teaches us is our best time is going to be when everyone arrives at the same time. See, I said at the same time, but I wrote simultaneously just to keep you guessing. Okay, so if everyone's going to arrive at the same time, that means I'm going to need some way to split it up evenly. So here's what I'm going to do. I'm going to label these two roads R1 and R2. Since the green one's at the top, I'm going to go ahead and label the green road Road 1. And I'm going to label the red road Road 2. I'm going to label them like that because I'm going to do some math with them, and I want to make sure that you can keep track of them as closely as possible. Okay, so I've got 200 cars, and I want them to be able to be split up evenly between them. So here's the thing. If I have two roads, one of them is twice as good as the other, that means that I've effectively got thirds. Think about it like this. So I've got road 1 plus, man, this looks a lot like Christmas, I just realized. Sorry. So I've got road 1 plus road 2. Okay, so that's going to equal 150. Because basically, my two roads can let 150 cars travel every hour. How much of that can the green road do? Well, the green road is able to handle itself out of the sum so many markers out right now. And in this particular case, this fraction happens to be 2/3. In other words, the green road can do 2/3 of the traffic of the entire road system. Does that make sense? So if we really want to use the roads as efficiently as possible, we should give that road 2/3 of the traffic. And if we do the same thing with a road 2, we should get 1/3. I'm not sure if I can put that on this page and it all fit without throwing you off. So if you like the way this looks, then just, I don't know, pretend I kept it like this. I am going to try to fit the other one in just for completion, and if I mess it up, remember this. Okay, so let me put a dividing line here. Okay, so this is kind of onto itself, and that's, yeah, there. Okay, sure, and then I'll that kind of worked. And the red road. Let me actually label this. That's the green road, the amount of the traffic that the green road can handle. The amount of traffic that the red road can handle is going to be its rate out of, oops, sorry, R2, out of the sum I get out of the classroom and I'm still obsessively uncapping and recapping markers. And that's going to equal 1/3. And that is the amount of traffic that the red road can handle. Oh, why did we do all that math? Well, the reason we did all that math is so that we could get all the traffic from the green road and all the traffic from the red road to arrive at the destination at the same time. That would be the most efficient use of the roads. So let me just throw another piece of paper on there real quick. We just need to know how long would it take for 2/3 of the traffic to go on the green road, and that should be the same as the amount of time it takes for 1/3 of the traffic to go on the red road. So I unfortunately chose a number that can't evenly be divided into thirds. So oops. However, that only matters for cars. So for voltage and current and stuff, that could be decimals. That's not a problem. So if I've got a total of 200 cars, and I divide that into thirds, each third of 200 is going to be 66.7, I guess we could say. It would be 66.6 repeating, but I'm just going to go ahead with that. And so we need to send 66.7 cars on the red road. 0.7 cars, I don't know what that is. That's like a Mini Cooper or something. All right, so and then we need 2/3 of 200 cars. That would be 133.3 cars. 0.3 cars could be like a motorcycle, I guess. And that's going to go on the green road. Okay, how long is that going to take? Well, 133.3 cars divided by the fraction 100 cars per hour is going to be 1.333 hours, or 1 hour 20 minutes. Okay, what about on that red road? So we've got 66.7 cars over 50 cars per hour. Turns out it's the same fraction. It's 1 1/3, rounding and all. And that's going to be 1 hour and 20 minutes. So if you were to send 200 cars over 2 roads, and let's see, here it is. If you were to send 200 cars over 2 roads with those capacities, If you send them all on the fast road, it takes 2 hours. But if you split up the traffic just right, you can get them all over there in an hour and 20 minutes. Okay, so this math is pretty complicated. Turns out that if you do a little bit of algebra magic, you can actually simplify these two roads into one road. So let me call that one road the total. Okay? So I could have one road which is the total. After you do all this algebra, the best way to express it is like this. The reciprocal of the combined total road is equal to the sum of the reciprocals of each road. I know that looks fairly strange, but trust me, that is the result of redoing all this algebra in general terms and then canceling everything out. I mean, you don't really want more math, do you? Tell you what, if you really want it, you ask me for it, I'll do it for you, but I'm just assuming that you don't actually want it. So that is how you could calculate the road capacity of the best possible combination of those roads given their two abilities to carry traffic. Hey, I chose the letter R because it was roads. Well, it turns out that this is actually the equation that you would use if you have two roads where you could split your traffic up between them. So there is a geometrical description for those. When you can choose between two roads, there's a term for that. They are in parallel. That's parallel. Okay, it's the same as the geometrical. Here, I'll write it real big and flashy and go to a new page. They are in parallel. There you go. So they are in parallel. And that is how you find the combined total ability for a circuit to carry a current when the resistance is in parallel. Okay, let's redo this scenario, but this time let's remove the choice. Point A to point B. You must travel on the green road, and then you must travel on the red road. No choice. The green road can still carry 100 cars per hour, and the red road can only carry 50 per hour. Okay, so in this scenario, if you've got 200 cars that need to go across that, it's going to take 2 hours, and then it's going to take 4 hours. It's going to take 6 hours, and there's just no getting around it. Okay, so if I wanted to find the total car carrying capacity of this road, how should I do that? Well, one guess is I could just add 150 and come up with 150, and then, well, wait a minute, that just got better. Okay, so in this particular case, this math isn't really very helpful. So the resistance of a resistor, the higher the number, the worse the traffic is. So let's do it more like in terms of a delay, right? So how about instead of 100 cars per hour and 50 cars per hour, let's say instead, if you take the green road, you're going to have a 10-minute delay. And if you take the red road, you will have a 5-minute delay. What will be the total delay? Well, if we had split the roads up, 10-minute delay and 5-minute delay, and done the math again, we would have done it basically the same way. But now, if you take a road that's a 10-minute delay, and then you take a road that is a 5-minute delay, you have got yourself a 15-minute delay. Okay, so in this particular case, the total road condition is going to be described as the simple sum of the two of them. So compare that to the equation that we had from the other page. That was all reciprocals. This is just a basic sum. This is the way it looks when you don't have a choice. You do one and then the other. You know, where one thing follows another in succession. There is a term for that, and that is called a series. When there is a series of something, it means it's one after the other. So when you do one and then the other, it's called in... Here, I did the other one fancy in another color, so I'm going to write this one fancy and big too. It's in series. Okay, so we've got two different ways of combining resistance in a circuit. We've got in parallel and in series. Let me draw a line so I can divide this up and put this kind of finally on this slide here. So when you've got two resistors in parallel, it looks like this. And you can approximate this as a single resistor if you add them together like this. The reciprocal of the total resistance equals the sum of the resistances of each resistor. This is in parallel. And let me do this in another color just for the sheer isolation of it. Separation, I mean. If you've got one resistor after the other, the total resistance is just the sum of each of the resistances, and this is called in series. And these are just two different ways that you can combine really any electrical component, but in particular resistors. It's just the first component that you end up adding up. So I'm going to prepare some really basic circuit combinations for you to do, and then we'll move on to something more complicated.